Good morning, everyone.
Good morning.
Okay. All right. So I posted an announcement on Moodle that will be having revision class during the lab time. And we'll be looking at our midterm 2 and also addressing some other questions, okay?
Is this just on a Zoom meet though?
Yeah, it's going to be on Zoom meeting, the same link we use for lectures.
Okay, thanks.
All right. So today we want to look at the second part of our chapter 12, and we'll be looking at extended discussions on thermal energy and how it applies to certain properties of materials. Remember, chapter 12 is talking about analysis of properties of materials as it relates to change in temperature and thermal energy influences. Okay, so we'll begin today's discussion by looking at thermal expansion. We have said so many things about thermal energy and some definition of terms to explain thermal energy and how they behave, and one of which is the thermal expansion. Okay, so let's picture the first established point in the last class, which is when we looked at the microstates of liquid, solid, and gas system of matter. We saw that in the gas, we have wide spaces between the molecules or particles of that makes up the gas. So that makes gas very easy to compress than compressing a liquid or a solid, because the particles or molecules of liquid or solid, they are closely packed. So to compress them, to compress gas is easier because it will take more effort to compress liquid and solid than gas. Now, in the same way, if there's a thermal change in a solid, liquid, or gaseous system, we will experience also certain changes in their properties that we'll be looking at with the term thermal expansion. Okay, so when you increase the temperature of a solid, it leads to a little expansion in that solid such that you will see a little or noticeable volume change. Okay, and also there'll be expansion in the linear dimension of such solids. So let's look at the figure before us. Just one example. All right. So we'll look at the figure before us. We'll see the box. Let's assume take this box to be a solid. We see the box at the initial state when it was cool. It has a temperature T1, and then it has the linear part L1, which we will later term as linear thermal expansion, that is the length. We'll have the volume V1 for this box when it was cooled. Now, when we applied heat, which is we transferred energy from this flame to the system, we notice that the system gets hot, right? As the system heats up, the temperature goes from the initial to a final temperature, a rise in temperature. And there's also an extension from the length, that is the little change in the dimension of the length and of that of the volume. Okay, so we see that with the application of supply of heat into this system, there's an increase, or what we term expansion, in the size of that system. It might be so little, but it is quantifiable. We can actually give a value to it. So when the focus is on the volume change, that is volume expansion, we refer to that as the volume thermal expansion. And the expression for that is the change in volume, which is the expansion, is equal to beta initial volume, the product of beta initial volume and change in temperature. Beta stands for the coefficient of volume expansion. So the coefficient of volume expansion multiplied by the initial volume and the change in temperature, that is the change in T, you know what that is, will be T final minus T initial, okay? So the product of those three will actually give us the quantifiable value that we're looking for, which is the change in volume. Now, if it's about the change in length, we're not just focusing on the volume. Let's say we'll have one, like a bar, a rod, there will be a slight increase in the length, right? So if our focus is on the linear expansion, the length, increase in the length, we'll use this formula, which is like a replica of the first one. That is the change in the length is equal to alpha, which is the coefficient of linear expansion, times the change in temperature as well. Okay, now this same point that we're talking about for an increase in temperature expansion can also be applied when there's a contraction. Okay, contraction really occur in solid when solid cools down. When it cools down, they shrink a little. So there's a change in their size, that's the volume. There's also change in their linear sides, which is the linear thermal sides. So for contraction, we also make use of the change in temperature, change in value, in volume, or this. Now, when there's an addition of heat and the volume is expanding in terms of increasing in length, we say it's positive, that process is positive. But when it is contraction, that process is negative, okay? So we should also take note of that sign, just like we are used to sign now and directions. So this is not new. When it's expanding, it's positive. When it's contrasting, it's negative, okay? So these thermal expansion processes have been experimented for different objects. And this is a table showing the coefficient of linear and volume thermal expansion at 20 degrees Celsius. We see that of glass having the linear thermal expansion, this with the units for the coefficient of linear thermal expansion and coefficient of volume thermal expansion being the same, which is per Kelvin, because we are actually measuring that in terms of temperature change, okay, by applying heat energy. So we'll have that of steel and iron to be the same value. And we'll have for concrete, we'll have for aluminum, we'll have for water for the volume, we'll have for ethyl alcohol and air plus other gases to have the same value, 3,400 times 10 raised to the power minus 6 per Kelvin. Okay, so let's see an example to see how we apply this to solving some problems. So we have the height of a Space Needle, a steel observation tower in Seattle, is 180 meters on a 0°C winter day. How much taller is it on a hot summer day when the temperature is 30°C? So we see, because this expansion and contraction is factored into construction, when they are constructing bridges, when they're making towers, when they're building the house, they factor this, what happens when it's winter and what happens when it's summer, because changing this temperature affects this material in terms of expansion and contraction. All right. So we see a construction, an observation tower that behaves in this way, applying the principle of thermal expansion. During winter at 0°C, its height is measured to be 180 meters. Now, at summer came, the height changes a little, okay? So we're not asked to know that length change. So apply this particular formula to solving our problem, because we're actually focusing on length, not the volume. Now, we saw also in our previous classes that change in the temperature of the Celsius scale is the same as change in the temperature of the Kelvin scale. So we don't have to, because if you convert to Kelvin, then find the difference, you still have the same value. So when we just give you a change in temperature, you use it directly. So the change in temperature here, applying the formula T final minus T initial, is going to be T final, which is 30 minus 0, will also give us 0°C. And if we know, I'll apply that standard knowledge that the change in scale of the Celsius and Kelvin is the same, it means this is also 30 Kelvin. Okay, so if we apply 30 Kelvin into the formula for the linear thermal expansion, we'll have this. Now, we'll have the coefficient of linear thermal expansion for, still from the table, iron and steel. So we see the value for iron and steel and concrete being the same. So for iron and steel, we use the value, which is the coefficient of linear expansion, and the initial length given to us, multiplied by the temperature change. So the product of these three parameters gave us 0.065 meters. So this is by how much taller this observation tower will be. So the new length is going to be 180 plus this value, okay? But we're asked to find how much taller. That means we're just asked to find the change in the length, okay? So we'll move on to the next, which is the specific heat and heat transformation. Now, specific heat is represented with the symbol C, and it's simply the amount of heat that raises the temperature of 1 kg of a substance to 1 Kelvin, okay? So no matter the substance you have, if you bring a 1 kg of that substance, the heat required to take that substance or change it from its temperature by 1 Kelvin is what we call the specific heat of that substance. So the specific heat of substance varies. The one for water is different from the one for steel and so on. We'll have established your standard values for specified materials that we use on daily basis. Okay, we will see that in our next table. Now, if having defined specific heat to be the temperature required to raise 1 kg of substance by 1 Kelvin, is the specific heat, and we said it varies from material to material. What happens if the material or mass of that substance is beyond 1 kg? So we say that the heat required to raise the mass of material M, the specific heat will be the mass of material M multiplied by the specific heat. That will be the temperature required at that point to raise that material by 1 Kelvin. Okay. So by that, we know that to raise the material to 1 Kelvin, there's also a temperature change. Therefore, the mass multiplied by specific heat multiplied by temperature change is the heat needed to raise the temperature of that mass M by that temperature change. So the equation to calculate the temperature required for the mass that is just above 1 kg is the heat being equal to the mass M multiplied by the specific heat multiplied by the temperature change. So the heat needed to produce a temperature change for mass M with the specific heat is given by Q equal to MC change in T. Okay, so that's how we calculate the specific heat or heat needed to change the temperature of an object using this equation. Okay, so we have also the table before us, which shows us the specific heat for some solid and liquid, which we'll be applying in some of our calculations or examples that we'll be seeing later. We see that of the mammalian body. The human body has the specific heat of 3,400 joules per kilogram Kelvin. The unit, this is the unit for specific heat. It is measured in joules per kilogram Kelvin. Okay, so we see that of water, and also we see noticeably that of ice. The one for water and the ice, you see that there are different values. So we have just listed 3 liquids. We have more than this table of specific heat, a standard like 4-figure table, standard table for specific heat of material exit. So an extract is just what we need, or because we'll be applying some of these in our examples. So the heat can either be positive also, and it can either be negative. I've said that when there's for system, when we define accelerated system, when the system is gaining, it's positive, when it's losing, it's negative. But in this case, for thermal properties of material, when there's a rise in temperature, the system is positive, it's having positive heat, and when the temperature goes down, the heat is negative. Okay? So let's also see how we apply this to solving problems. A student catches the flu and his body temperature increases from 37, which is the normal body temperature, to 39. And this is the equivalent temperature in Fahrenheit. So because the student catches the flu, the student that is weighing 70 kg catches the flu, the body temperature changes. The question now is how much energy is required to raise his body temperature? For there to be a temperature change, it means an energy has been applied that brought about that, okay? So the question is now asking us to find the amount of energy required or that was used to change the body temperature of that student. So the first thing we note in the question is the change in temperature. The change in temperature is the final minus the initial, which is 39 minus 39 minus 37 gave us 2, which is 2 degrees Celsius. Okay. What I'm writing is not clear. Let me rewrite that. So I have 39 degrees Celsius minus 37 degrees Celsius gave us the 2 degrees Celsius. And going by the temperature, the change being the same for the scale, Kelvin and temperature, Celsius scale, we have also that for Kelvin change in temperature is going to be 2 Kelvin as well. So our change in T is 2. The specific heat of the human body, as we have seen in this table, the previous table we saw here for human body is 34 joules kilogram per Kelvin. So if we use that value to solving our problem, we have that the energy, which is the heat energy required, is equal to the product of mass, specific heat, and change in temperature. So the mass is given in our question to be 70 kg, the mass of the student. Then we'll have the value, standard value of our specific heat multiplied by the change in temperature to give us 4.8 times 10 raised to the power 5 joules. So that's the amount of energy required, but that the body has used to change the temperature of that student. Okay. So let's look at another interesting part of the properties of material and how they influence the change, thermal changes, thermal energy changes. The term we want to look at now is called the phase change. Now, the phase change talks about the change of matter from a particular phase, either liquid, solid, or gas. That change of a matter to liquid, from solid or solid to gas, or liquid to solid is what we refer to as phase change. Okay? But the phenomena of phase change is what we now want to look at a bit in details. Let's look at the image before us. Suppose you take an ice block from your freezer and you put in a sealed container. The image 1 to 5 is what we want to use to explain this particular concept of phase change. We have already basically established that phase change is talking about melting, freezing, and vaporization, okay, which is liquid, solid, gas, and changing from one phase to the other. So if you take an ice, which is one of the easiest that we can look at quickly, you put it in a sealed container, you apply certain amount of heat such that the heat applied is steady. You see that if you put a thermometer reading, at the initial, it's going to read a level, a temperature level. Then as you apply the heat, you notice that the ice begin to shrink, as we see in figure 2, and you begin to see some liquid in that container. You are still applying steady heat. But the unique thing about these two phases is that as this is changing from ice to liquid, the temperature is still the same, regardless of the steady heat applied, right? So we know that the freezing point of water is 0. So if it's at 0 degrees Celsius, you have 0 degrees Celsius here, and you also have 0 degrees Celsius here for both. So the ice is beginning to melt into water. And if you keep applying the steady heat, a time comes where you will not see any ice at all. You see that the ice has melted, everything is now water. And the heat being applied will keep raising the temperature of that water until it gets to its boiling point. So the temperature measured here will begin to vary from 0 as it tends towards 100. So it's going to go from 0 200. That is the initial freezing point, 200. So it's warming up. And then if you keep heating, you keep the steady heat being applied, it begins to steam. When it gets to that 100, it begins to boil, and then it begins to give out gas, and the volume begins to reduce until everything steams as seen in figure 5. Okay, so we see that the temperature is as a function of time that the heat is applied. So the water transformed from solid to liquid and to gas as a function of time. So the transformation took place over time that heat was applied. Okay, so we have from this process some terms that we'll have to define, such as the melting point. Okay, I'll find a way to put it in the different slide when I'm uploading the final version, so that, but it's better you put it down now, in case when you're reading, you will not say it's not in our notes. So we have the melting point. The melting point is actually the temperature at which, if the thermal energy is increased, a solid becomes a liquid. At that point, we say it is the melting point. Okay, every material have their melting point. The melting point of water, the melting point of solid, the melting point of steel, and so on. So the temperature at which also the liquid will become solid is the freezing point. Okay, then we'll have a temperature whereby the liquid and the system at the melting point is having the same temperature, the zero with, like as we see in the image 2. At that point, we'll have what we call phase equilibrium. That is the melting point where there's no change in temperature, and that we can easily see in the graph of figure B. We see the first stage, the slope, but at the second stage where the temperature is not changing, it's just, transforming from solid to liquid. You see it's flat, horizontal. The temperature is constant. This is one of the phases we refer to as phase equilibrium, and this is another one that we refer to as phase equilibrium, when it was now going from liquid to gas, as we see in the stage 4. Okay, so we'll see the graph of the different phases giving us different explanation of what we mean by phase equilibrium. All right. So we see that a phase change is characterized by a change in thermal energy. All right, without necessarily a change in temperature, because we see that in terms of the ice becoming a liquid, the temperature at 1 and 2 remained at 0. There's really no change in that temperature. So phase change is dependent on thermal energy change, not necessarily temperature change. The temperature, we know what the thermal energy is talking about, is referring to the sum of kinetic energy being brought into the system, as we have seen before. Okay, so we have defined the freezing point, the melting point. We want to look at the condensation point. That is the point where the gas becomes a liquid. It is called condensation point. And so the pair for that is boiling point. When a liquid is going to gas, the liquid is changing to gas. It is called boiling point. So in this figure 1 to 5, we can see the freezing point, we can see the boiling point, we can see the melting point, we can see, the condensation point is not apparently displayed, but if this vapor that leaves this is cooled down or captured and cooled down, it goes back to liquid, then we'll be able to describe a phase called the condensation. Okay, so you take note of that: boiling, freezing, condensation, melting, phase equilibrium. Those are the 5 things to remember when it comes to phase changes, okay? So we move on to another part, which is the heat of transformation, okay? Now we are seeing L in many forms as the presentation of coefficient or linear thermal coefficient and so on, but don't be confused. As long as your parameters is defined, some textbook did not use L, but in our current test, we are using L. So the amount of heat energy that causes 1 kg of a substance to undergo a phase change is what we call the heat of transformation. So heat of transformation is simply describing phase change as it relates to the amount of heat energy required. Okay, we saw the application of heat energy as the steady flame applied under those containers. So the heat required for the entire system of mass M to undergo a phase change, that is to change practically from liquid to solid or solid to gas, is given as Q equal to mL, L being the heat of transformation. Okay, so you see that we are just using the word heat of transformation in a generic term to describe or quantify the heat in a phase change. So for that, which we have defined as Q equal to mL, when it is about freezing, melting, we're using F, which means the heat of fusion. So it is plus or minus, because it's either cooling or increasing in temperature. So that's why we have the plus or minus. The plus or minus mLF to represent the fusion, and we use V to represent the heat of vaporization when it's going from boiling. Phase change is about boiling or condensation. So we see these 2 pairs, melting, freezing, boiling, condensation, for different masses of substance. Okay. So that principle also has been applied, and we'll have standard or constant values for the boiling point, melting point, freezing, condensation point at different. The clear one is that of the water that we know. We see that of the water melting is 0, 4, and you see this, the heat of fusion is also given to be 3.33 times 10 raised to the power 5 joules per kilogram. We have also the boiling point for water to be 100 and the heat of vaporization to be 22.6 times 10 raised to the power 5 joules per kilogram. So
can I just ask, like, heat of fusion, what does that mean, like, specifically? I just want to check.
Okay, the heat of fusion, like we see here, is that heat transformation or the quantity of heat required, okay, for a solid, a liquid or a solid like ice to become a liquid, or for a liquid like water to become ice, which is solid. The heat required to make that phase change is what we call the heat of fusion. Okay.
Okay, thanks.
All right. So we see that clearly in this phase. Okay. We're applying certain steady heat over time to give us that. Okay. All right. So we want to see an example. And then we'll be looking at the last one. We'll have 2 to go. A girl eats a 45-gram frozen popsicle, like the ice cream on a stick, that was taken out of a minus 10 degrees Celsius freezer. How much energy, whenever we talk about this, we're referring to heat energy, okay? How much energy does her body use to bring the popsicle up to the body temperature? Because as she's going to be eating the frozen ice cream in a stick called popsicle. It's going into the system. The body is doing a kind of heat transfer to bring about a phase equilibrium, because it's going to dissolve using the heat, the body heat. And we'll have the standard value for body heat, okay, which we have seen in our previous table. We'll just be taking the values from there. If you're giving such questions in an exam, the value will be provided as one of the constants on the formula sheet, okay? So you don't have to memorize them. So the solution to that, which we are asked to look for the heat, is that we specifically first note the change, and then we notice that the first phase, when the girl eats the ice cream, it will melt, right? So we use this equation for the heat change, M multiplied by the specific heat of ice, which is giving us 20 times 10, 2090 joules per kilogram Kelvin. And then we'll have the change, which is the final. The change is given. We know that it's going from 0 to minus for freezing. So we'll have the change to be 10. We take the absolute value. So that's how we'll have our 10. 10 degrees Celsius is also the same thing in terms of change of temperature as 10 Kelvin. So we'll apply that directly to get the 940 joules. So you notice that because it is ice, it's frozen, we have to use the specific heat for ice instead of water. Okay, so, and then we'll have the mass in gram, we converted to kilogram. So that's how those values became what we saw on that part. So the next transformation that occurred there is the heat. It goes from ice to liquid. We use the heat required, which is the heat of fusion. So, which is given as Q equal to ML. For fusion, we use MLF. And that for fusion for ice is given as this. We'll have it stated here, water, when it freezes, because the popsicle is like a flavored water. Okay, so we still use the value for water for it. So we also multiply that to give us 15,000 joules. Now we approach the final question, which is the amount of the heat, how much heat is required for the body to do that. So the liquid water, when the child takes it, now warms up by the body temperature, and the standard body temperature is given as 37, okay? So that's where we got that 37 from. So we'll apply that to the same, so we'll have 3 phases of heat change here, Q1, Q2, Q3. When we apply that, we got 7,000 joules. So the total, which is the net heat of that system, is what the heat energy that the body used to take that.
I just want to check, what is Q2 is representing which phase change?
It's representing the fusion, that is, it's going to from ice to water. At the ice,
what's the first one?
This is at the ice.
Okay.
Okay, so this is where it goes to water, liquid in the child's mouth. And this is where it heats up. Okay, so we see how it's going to liquid and it heats up, just like we saw in the first 5 blocks that we saw. It's the same process that is happening here, but it's happening in the system of the child. Instead of applying a steady heat, the body temperature is the heat supplied. So it goes from ice to liquid, then heats up. Okay. So we now take the total heat, summing Q1 plus Q2, we call it Q net, or total heat, which is Q1 plus Q2 plus Q3. It gives us this but in your test, you're going to see it as 23,000 joules. It is approximated to the 263. Okay, so we'll look at the second to the last because we have just the last is calorimeter. We look at the term vaporization. Vaporization is popularly seen when a liquid is boiling. That is, it's going from liquid to gas. And for water, it happens at 100 degrees Celsius, okay? But we also experience vaporization when there's really no change in like a supply of heat energy, just like you see when you sweat, you cool off by vaporization, you heat up as well. Okay, so what happens is that individual molecules of water can move from liquid to gaseous phase, even at low temperature. And we've just given an example of sweating. You are not at 100 degrees Celsius, but when you sweat, the sweat can dry up, right? It means vaporization can actually occur at temperature less than 100 degrees Celsius, okay? So, but the process or phase change that involves the movement of liquid to the gaseous phase or gas is what we call vaporization. All right. So we also now have that the heat to evaporate a mass M of water is given by this. You remember the fusion and look at it, vaporization. Okay. So that's where we are bringing that V from. So you have seen this equation before. It is not new. We're just using it to define the term where it applies in movement of liquid to gas. For fusion is for liquids to solid and solid to liquid. Okay, that is freezing, melting. And then for this one, we have vaporization, condensation, or boiling point condensation. Okay, so we have the standards. Reason why we have to specify this is because we're going to use it in the next example. The skin, which we have already stated that is one of the examples where vaporization occur at low temperature. It actually can occur at the temperature as low as 30 degrees Celsius. The molecules of water that you produce from sweating can go into vapor at this temperature, which is a temperature far less than the body temperature, right? So that's why we refer to it as low temperature. So we have that to be this, and the heat or at that stage is given with this value. Specific heat at this is 24 times 10 raised to the power 5 joules per kilojoules. Okay, so let's see that in a quick example. Then we'll look at the very last one. The human body can produce approximately 30 grams of perspiration per minute. Okay, so at what rate? See the word rate. Whenever you see rate, it's talking about the time factor as it applies to the term in question. All right. So we'll be looking at that because we did not state a particular formula with the rate, but we'll see that in this example. So at what rate is it possible to exhaust heat by the vaporization of perspiration? The information supplied there is just to help us answer the question. The water is evaporated from the skin, which we assume to be at this temperature, and the value for the heat of transformation, LV for vaporization, is given at this value, which we have seen earlier, and that is why we established it here, because we want to use it here. So the solution, the question is at what rate? So we'll begin solving this problem by first converting our gram to the standard unit kilogram, which will give us 0.03 kilogram okay? So the vaporization of 30 grams of perspiration at the normal body temperature, which we already know what's our normal body temperature. It's 70 for this gram, but our specified temperature there is 30. So we have the equation, which is the Q, energy required for the heat energy of transformation, to be the product of mass, as given in the question, times the constant of the transformation energy for vaporization, to be 7.2 times 10 raised to the power 4 joules. So this is the heat of vaporization, or the energy heat that brings about the perspiration as specified by the human body. So when we want to look at the rate, we're actually specifying it per time. What is really going to happen in a minute or a second? Okay, so we'll have that the heat loss per minute is going to be Q over the time taken for that heat to be lost. Our Q is given as this, which we have solved, and then time is 1 minute is 60 seconds. So we'll have the rate for that to happen, to exhaust the heat for vaporization of the sweat you get at that temperature, to be 1,200 watts. So Q over change in T for a minute, which we now use as 60 seconds, gave us 1,200 watts. So this is the equation we use to calculate the rate for heat of transformation for a system. Okay, so we'll look at the very last part of our class today. We just have 3 minutes to look at it, calorimeter. Calorimeter is simply the measure of, or the way we quantify the heat energy, the heat transfer energy, the heat energy for transfer or transformation of what we see like phase change, ice to liquid. When two systems are in contact, we quantify how that one can actually transfer heat to the other and bring about a phase equilibrium in that system. Okay, so calorimeter usually occurs between more than one system. And then it's usually clearly seen when the system is isolated. So we see, for example, the ice dropped, which we do every day. When our tea is too hot, we drop, or when you want to take cold drink, you just drop in ice from the freezer to the drink. You don't have to freeze it. Then you expect a kind of transfer of heat, right? You expect that the drink will get cooler when you drop ice. Or when you heat it up, it's going to get warm. So you see, the calorimetry is actually the quantification measurement that is done to that process of heat transfer. Okay, so we say that the quantitative measurement of heat transfer is what we refer to as calorimetry between systems that are interacting, or majorly between system in interaction, bring about heat transfer. So now this is what we do every day, but this action that we take every day can actually be quantified. So we see that the system one, if we say the system one is the one that is giving out, when it is gaining, the one that is gaining, and when it's giving out, it's minus. So, but actually what is happening is that the magnitude of the heat given off is going to be equal to the magnitude of the heat gained by the other one. The sign is just to tell you which one is gaining and which one is losing, okay? So as heat is being transferred from system one to system two, you notice that the heat is increasing in one and it is decreasing in the other. So we see that also in the image two here, where we have two systems, system 1, system 2, energy is moving from system 1 to system 2. We will have a state where we have the net energy to be the sum of the energy of system 1 and system 2. They will reach a state that nothing changes. Where we have the phase equilibrium, the heat energy at that state is conserved. So it is equal to 0, it is constant. Okay, there is no longer a time will come, ice will melt completely into this. You will not notice any temperature change. The system will have just one temperature, which is referred to as the net temperature. We'll have the strategy of solving problems. It's the same step that we've been applying. This is the very last example. 2 grams of unknown metal is heated to this temperature. And then it is dropped into 50 grams of water at 20 temperature. Look at the solid 20 gram heated at high temperature. Then they want to cool it. They quickly drop it into a cool water of 50 gram at 20 degrees Celsius in an insulated container, so that the heat exchange is happening between the water and the metal. It's not really going off into the environment. So then we can quantify the heat transfer. Okay, so they gave us the parameters and told us that the temperature of water actually raised from 20 to 27.7 degrees Celsius, which is, we can find a change here. And they're asking us now to identify the metal. To identify that metal, you have to have like a table. After doing your calculation, compare the value you have to the metal detail. Then you'll be able to say, oh, from this calculation, this is the kind of metal that was thrown in it. Okay, so we just use this to define the time, the initial temperature of the metal, Tm, for that of the water, and the final temperature for both when there is like a thermal equilibrium. The system both have no more exchange in heat. So we'll have the standard specific heat for water, and the specific heat for that metal is what we don't know. So if we can find the value of the specific heat of that metal, we'll go to the specific heat table, we'll see the metal that carries that value, and we'll say that is it. Okay, and if we see two values having the same, we can say this is either this, like A or B, because they have the same value. Then there are other tests to further verify the exact metal. So apply the conservation of energy as we just saw, which is the sum of the energy of the system being constant. We'll have, using this is just the full expression of the Q equal to MC change in T. All right. I've taken about 3 minutes extra from my time. I really apologize for that. So the parameter, we just made this the subject of formula to get this equation. All the parameters are supplied in the question. This is the standard WCW, and this was supplied for water because we took that of water plus that of metal. So with the information, we just input them directly to get this. And we went to the table to compare, the specific heat table, to compare our value to what we have. So we saw that the metal is either gold or lead. Okay. Thank you. So this classwork, because I know that we might not really look at it, the answer has been supplied here and the reason for the answer given. So I expect to see us back in class by the lab time, which is 1:40, and it's going to be online. We're using the same link, okay? We'll be looking at the test question. So for those of you who sent me email that want to meet to discuss things about the test question, we'll do all that by noon lab time, okay? Are we good? Do we have comments?
Hi, actually, I have a question. So is this only for the Wednesday lab or will you also have one for Friday?
Only for Wednesday. There will not be a section for Friday because I will not be available on Friday.
Okay, sounds good. Thank you.
Thank you. Okay. Are we all cleared?
I have a quick question.
Okay.
For Friday's lab, I was wondering, could you record this meeting today and then upload it for Friday?
Of
just
course.
So we can have a sense of what happened?
Yes, definitely.
Okay. Thank you.
And if you have questions, you know how we did it the last time. I might be online, but not really going to be fully online like I'll be on Wednesday, this today. Okay. Mm-hmm. Okay.
I was wondering if you could post last lecture, like our last class, like on the YouTube of our classes recording.